Hello, I'm Seema and welcome to part 2 of the chapter Chemical Kinetics. I told you in part 1 how important it is for us to know how fast or how slow a chemical reaction occurs. And if we know how fast or how slow it occurs, are there ways that we can use, or are there ways how we can alter the rate of a chemical reaction according to our needs? So that is the need for our knowing chemical kinetics. In this video, I'm going to talk about these rates of chemical reactions and how do we calculate this rate. When we talk of rate related to speed, imagine if you were to calculate my speed. I was walking from this end of the board to that end of the board, and I was taking my own time, and I'm talking to you and I'm taking my own time. My steps are really small and I took so much time to cover this distance. So what would you say about my speed? And now for the second time when I'm moving from this end to that end again, I do it in one jump. So when was my rate faster? When was I faster? How did you come to know that the second time I was faster and the first time I was moving slowly? It was by the distance that I covered and how much time did I take in covering that distance. The distance was the same in both the cases. The only difference was in the time that I took to cover that distance. So that gives you the idea of speed or rate. So when we're talking of objects, moving objects, and talking of speed, it is distance traveled upon time taken. But in a chemical reaction that is occurring in a beaker, nothing is moving from here to there. So how do you apply that concept to a chemical reaction? Let us understand that. What happens in a chemical reaction? Initially, you have a reactant, and one reactant or more reactants, and they react in order to give you the product or products. The product may be one, or you may have multiple products. Now, the reactant, initially when the reaction had not started, you only have the reactant. Therefore, the concentration of the reactant is highest initially. But as the reaction proceeds, the reactant is being used up to form the product. And initially, the concentration of the product was 0. So as the reaction proceeds, the concentration of the reactant goes on decreasing, while the concentration of the product, which was 0, starts increasing. So in a reaction, we do not see what is jumping from here to there. We check the concentrations. What is the change in concentration that is occurring? And when we talk of speed, time is a factor. When you talk of rate, time is a factor. So how much of concentration changed in how much time will give you the rate of a reaction? It's simple logic. How much time took for this reactant to change from this concentration to this concentration, and divided, so the change in concentration divided by time will give you the rate of reaction, right? So let us take this example, and then there's one factor here. There's a negative sign that we have to use, and I'll explain why we do that. You have the reactant, it is turning into product. If there is a change in time, you have two times. Initial time was T1 and final time was T2 when you're calculating the rate. T1 and T2, the change in time would be delta T, which is equal to T2 minus T1, which means final time minus initial time. R in box brackets means the molar concentration of the reactant. So the molar concentration of the reactant, the change in molar concentration of the reactant would then be, if R2 is the final concentration and R1 is the initial concentration, then R2 minus R1 will give you the change in concentration of the reactant, which is known as delta R. And if you take the concentration of products, P1 is the initial concentration of products and P2 is the final concentration of products. Then the change in concentration of products would be P2 minus P1. Understandable. Now what is the rate at which R, that is the reactant, disappears? If you're talking of rate in terms of reactant, if you say initial concentration of reactant and final concentration of reactant, I told you as the reaction proceeds, initially the concentration of the reactant was the highest. And as time passes, the reactant is being used up to form the product. Therefore, the concentration of the reactant is constantly decreasing. So, whatever is R1, that is the initial concentration of reactant, and R2 will always be less than R1. The final concentration will always be less. Why? Because the reaction is proceeding and the reactant is being used up. So when you find out delta R, the change in the concentration of the reactant, we say R2, which is smaller, minus R1, which is a higher concentration. So you will take a smaller concentration and subtract a higher concentration from it. So numerically, you will get a value which is negative. Numerically, you will get a value which is negative. What does it signify? That this much of concentration has decreased. There is a decrease in the concentration. But rate cannot be a negative value. When we say rate is change in concentration divided by time taken, then if we have R2 minus R1 is a negative value, then R2 minus R1 upon delta T will also be a negative value, and rate cannot be negative. Therefore, whenever you are talking, whenever you are reporting rate in terms of reactants, we put a negative sign so that the value of the rate always comes out to be positive. If I am walking from here to here, whether I am walking slow or I am walking fast, my speed always is positive. It cannot be a negative speed. How would it be a negative speed logically? So, rate cannot have a negative value. Therefore, whenever we talk in terms of reactants, we have to put a negative sign there, right? So, if we talk of rate in terms of reactant, then rate of disappearance of the reactant, we are talking of the rate at which the reactant is disappearing or being used up. So, it would be the decrease in concentration of the reactant upon the time taken. And how would you show the decrease in concentration or change in concentration? Change in concentration is R2 minus R1, and therefore you will use a negative sign so that the rate has a positive value. If we want to calculate the rate of a reaction in terms of the product now, the product initially had a concentration of 0. Now these are two curves which show you, this is in terms of the product versus time, and this is the concentration of reactant versus time. So do you see in the case of reactant R0, initial concentration at T0, initially at T0, the concentration of the reactant was R0, which is the highest. As time passes, T1, T2 time is increasing here, the concentration of reactant goes on decreasing. So when you have to find out the value of when you are calculating the rate of this reaction, it will be R2 minus R1. Let us take 2 points. This is T1 and this is T2, and this curve has been plotted by taking the concentrations at different times. That at T1, what was the concentration of R0? At T2, what is the concentration of R0? At T3, T4, T5, T6, T7, T8, T9, we keep plotting the dots. We plot the dots and then we join the dots to get this curve. So if you want to find out the rate, what do you have to do? What was the concentration at T2? At T2, the concentration is R2. And at T1, the concentration is corresponding to it. See, the concentration is higher. So, because the concentration of the reactant was decreasing, so R2 minus R1 upon T2 minus T1 will give you the rate of the reaction in terms of reactant. But since R2 is smaller than R1, you cannot have a negative value, you will have to use a negative sign for the rate. Now look at this curve. The product initially was 0. The concentration of the product is 0. As time passes, the concentration of the product goes on increasing. So when you have to calculate the rate of the reaction between T2 and T1, we will find the corresponding points on the curve. At T1, the concentration of the product is P1, and at T2, the concentration of the product is P2. So P2 minus P1 upon T2 minus T1 will give you the rate of, now P2 is greater than P1, so the rate, you will get a positive value of the rate of the reaction. So whenever you are writing down the rate in terms of products, you do not need a negative sign. You just write the change in concentration of products, or delta P upon delta T, which means P2 minus P1 upon T2 minus T1. Now this way of writing down the rate is known as the average rate. You are taking down because in the curve you took 2 points, any 2 points, and then you found out on the average this is the rate between these 2 points. This was the rate of the reaction, and whatever was the path of the curve, you're not concerned. You're only talking of this point and what would have been the average rate during this time period. Average rate of the reaction. Now let us say for a particular instant of time, for one particular time, let us say time t, it's a fixed time, and you want to find out the rate of the reaction at a fixed time, not between T1 and T2. At that particular instant, you are interested in knowing right now, in this moment, what is the rate of the reaction. Such a rate of reaction in which you want the rate of the reaction at one particular instant is known as the instantaneous rate of reaction. In that instant. So you will again look at the same curves for both the products and the reactants if you have to calculate the instantaneous rate. The method is the same. The change in concentration in that instant, the change in concentration of the reactant or the product divided by the time taken. And if it is reactant, you will put a negative sign. If it is product, it will remain a positive sign. But the change in concentration of the reactant in one instant is going to be minuscule. You're not going to be able to observe it. It's not going to be easy to observe it. So what do? In the graph, you take that point and you draw a tangent to the curve. A tangent is a straight line which touches a point on a curve. That's known as a tangent. So you, at that point T, wherever the curve is, you will draw a tangent to it. Like I drew a tangent here, and on the product side, we took T and we drew a tangent like this. Now the tangent is drawn in such a way that you move equal distances on both the sides, which means if you take in terms of time, you're going equal. If this was, let us say, there is one example here you have. That is, you have to find out the instantaneous rate of a reaction at 600 seconds. Right? So what did we do? We drew a tangent, and the ends of the tangent are 600 was that point, the central point, the time at which we want to know the instantaneous rate. So we draw the tangent in such a way that the tangent extends to two readings on the sides, that is 400 seconds and 800 seconds. The change in concentration at 400 seconds and 800, that is 200 seconds this side and 200 seconds that side. Now, when you have the tangent drawn extended on both sides equally, we now extend it and make a right angle. And we'll get a right angle triangle. Now, this distance, when you join these two by drawing perpendiculars to it, you will get that this distance is the change in the concentration of the reactant taking this example, between 400 seconds and 800 seconds. And the change divided by dt. So dt in this case would be these 2 points. That is the base of the right angled triangle. And dt, so this again, time is also extending from 400. We were looking for 600 seconds. We extended it to 400 seconds, extended it to 800 seconds. So the time now becomes 800 minus 400, that is a difference of 400 seconds, and whatever is the change in concentration using the tangent and not the actual curve. Measure that and substitute that value. So that gives you the instantaneous rate of a reaction. So R instantaneous is equal to, in the case of reactant, would be minus D. Small d is small change, small difference, small change in the concentration of the reactant. That is dR, and divided by T2 minus T1 is dt, right? dR upon dt. And which means that this is, what is our instantaneous equal to then? According to your mathematical knowledge, this is the negative slope of the concentration of the reactant. This is the negative slope. The negative slope will give you the instantaneous rate of reaction. At the same time, we could have found out the instantaneous rate of reaction using the products also. Let us say T was the point at which we had to find it out. So T we plot it here, we draw a tangent equally on both sides and again form a right angle triangle. This time it is inverted, but it is the same. This point to this point is the difference in time, and this point to this point will give you the change in concentration of the product. Again, small dP over dt will give you the instantaneous rate of reaction for products. Only you will not put a negative sign because the concentration of products is increasing and you will not get a negative value for the rate of the reaction. Now there's one example given in your book, in your textbook, where C4H9Cl plus H2O gives you C4H9OH plus HCl. You've been given different concentrations and different mathematical values for times and the concentrations. And honestly, the mathematical values and that table in explaining right now is not that important. What is important is for you to understand that a curve is formed and every point has a certain mathematical value that is in every concentration at every time, and that will give you a curve when you join all those lines. On the basis of that, then in the book they explain that if you have to calculate R average, that is the average rate of reaction, it would be equal to minus of change in concentration of reactant upon change in upon the difference in time. So, or upon time taken, which is equal to the change in concentration of products upon time taken. That is delta P upon delta T, which is equal to minus delta R upon delta T. And when T tends to 0, that is the difference between when delta T tends to 0. When the difference in temperature in time is almost 0 or it is instantaneous, we calculate R instantaneous, which is equal to, in terms of reactants, is minus d R concentration of reactant upon dt, which is equal to the dP, that is change in concentration of product, upon dt, which is change in time. And as I told you in the book, that particular example, I just wrote down this one with the values so that you understand, and if you do not, please refer to that example in the textbook. R instantaneous, we had a curve like this and we wanted T was 600 seconds and the values of R1 and R2 were according to this tangent, the two corners of the tangent, and the corresponding values were seen and they turned out to be, this was R2, this was R1, and it will have to be a negative value if it is the reactant, and upon 800 minus 400 if it is reactant, we put a negative value here. I'm not sure how was it in the book, was it with regards to reactant or was it with regards to the product. If it was about the reactant, you'll put a minus sign here. If it was the product, you'll let it remain positive and you'll get the rate of the reaction. Now, there is one more thing to understand when you're talking of the rates of reactions. When we are using this formula, that Hg plus Cl2 will give you HgCl2. This is another equation. So how would you write down the rate of the reaction in terms of each reactant and each product? If we are talking in terms of mercury, rate would be the change in the concentration of mercury. It will be a negative value. Why? Because it's a reactant. And whenever we are calculating the rate in terms of reactant, we have to use a negative value. So it will be minus delta Hg upon delta T. In terms of chlorine, it will be minus delta concentration of chlorine upon delta T. And in terms of this product, it will be a positive value. So positive HgCl2, concentration delta HgCl2 upon delta T. Now we take chemical equations which have different stoichiometric coefficients. That is, you do not have unimolar, everything is not single moles. How does that affect your calculation of the rate? You have 2Hi giving you H2 plus I2. So when we said that rate of a reaction is the rate of change of concentration of a reactant divided by the time taken. Now, if you really look at this, you get Hi, 2 moles of Hi are being used up. When 2 moles of Hi are used, 1 mole of hydrogen and 1 mole of iodine is formed. So when I am calculating in terms of the decrease in concentration of HI, the decrease in concentration will be double because it's not 1 mole, 2 moles are being used. When we had two different reactants, it was easy to understand that rate can be calculated for any of the reactants. But when the reactant, the 2 moles are actually of the same compound, then to you it will appear that the rate of reaction when you're calculating in terms of reactant will be double, because the rate of using up of HI is twice, because 2 moles is being used up. And while only 1 mole of hydrogen and 1 mole of iodine is being formed. So if you calculate in terms of hydrogen and iodine, you will get change in concentration of hydrogen upon delta T will give you the rate. Change in concentration of iodine upon delta T will also give you the rate. But change in concentration of HI would be double. So you will get a different rate of a reaction. When you calculate for any reactant or product which has a different stoichiometric coefficient other than 1, which has more than 1 number of moles. In that case, what should you do? Because rate cannot be different. The speed, a car went, okay? The speed of the car, it took this much time to go from point A to point B. There's a joke, you know, that a person goes and he climbs up a bus and he sits in the front seat. He says, no, he fights with people and he tells, no, I will sit in the front seat. So they ask him, why do you always want to sit on the front seat? What is it about the front seat that you always have to be there? He says, because I'm a very competitive person. And since I'm so competitive, I have to come first. So I will be the first one to reach that place. While the whole bus is moving and there's all the passengers are going to get there at the same time, yet he feels that he's in the front. So he thinks, does he think that his rate of reaction or his speed at which he reached would be different? No. So when you calculate the rate of reaction using different reactants and products, you must get the same rate, because after all, the reaction is taking place at the same rate. So what correction should you do? Whenever you have a stoichiometric coefficient which is other than 1, you should divide the rate by that coefficient. Right? By that stoichiometric coefficient, you divide it. So if 2 moles of HI are being used up, you will say 2 divided by 2 would be 1 mole. And then 1 mole of this, 1 mole of this, 1 mole of this, then the rate when you calculate it would be equal. So there is one more example, a little more complex here, not really complex, where they've used different stoichiometric coefficients for you to practice this. The equation is that 5Br negative gives you BrO3 negative plus 6H positive will give you 3Br2 plus 3H2O. Now, let us write down the rate for this. The rate in terms of all the reactants and rate in terms of all the products for this reaction. So what will rate be? Rate will be equal to minus the change in concentration of the reactant Br negative divided by its stoichiometric coefficient. So it will be minus, because it's a reactant, 1 upon 5 because the stoichiometric coefficient is 5, change in concentration of Br negative, molar concentration, upon delta T. In terms of BrO3 negative, it will be equal to, since it's a reactant, minus change in concentration of BrO3 negative, molar concentration, so box bracket, upon delta T. Now, we do not divide it by any stoichiometric coefficient here, because it has the stoichiometric coefficient here is 1. And in the case of 6H positive, we'll write it will be equal to minus 1 upon 6 delta H positive upon delta T. And in terms of the products, how would you write it now? Which would be equal to 1 upon 3, because the stoichiometric coefficient is 3. We'll keep it positive because it's a product. Change in concentration of Br2 upon delta T, which would be equal to Again, the stoichiometry coefficient is 3, but it is a product, so no negative sign, but 1 upon 3 delta change in concentration of water upon delta T. Now listen, whenever you have gases as reactants or products, you cannot talk of the concentration of gases in moles per liter. So in case of gases, the concentration is directly proportional to its partial pressure. So whenever you have gaseous reactants or products and you're supposed to calculate the rate from gaseous reactants and products, instead of using delta C or change in the concentration, you will use delta P, where P is the change in the partial pressure of the gas. So you can calculate the value of the rate of the reaction even if you calculate the change in the partial pressure of each component, if it is a gaseous reactant or a gaseous product, right? So this was how we calculate the rate of a reaction. And with this, I'll finish today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.